Oh, I'm not the host.
Oh, Steve has to record it.
You have to have Steve record.
I just started recording. Yep.
Perfect.
So today, in the last lecture of the course, we're going to be discussing how to train neural networks. Finally. So we have been discussing the math behind neural networks and the theoretical aspects, but let's say around 60% to 70% of training deep models has nothing to do with the theoretical aspect. It's an art. It's experience. It's trying different things. It's knowing what's happening when your system breaks, right? So a good machine learning practitioner would need to know how to choose an algorithm for a particular application and how to monitor and respond to feedback obtained from experiments in order to improve a machine learning system. This is very important because as we will see, the machine learning system, our deep learning system, can break on many different aspects, in many different ways, that we need to know what's happening so that, right? So during our day-to-day development effort, we need to know when to, for example, collect more data, increase or decrease the capacity of our model, add or remove regularization, improve the optimization algorithm, or simply just debug the software implementation of our It's really time consuming, as you guys know. And it's very important for us to know exactly what went wrong so that we don't end up spending days and days on debugging issues that are not the reason behind our actual model break. And of course, in practice, one can usually do much better with the correct application of a common-based algorithm than by slowly applying an obscure algorithm. What does that mean? That means that who knows who this guy is? Occam. That's Occam's razor. Simplicity. It's like if there are many solutions, the simplest one is the one that's favored. Sometimes you don't even need deep learning to solve your problem. Do not assume that you just, like deep learning is a black box, magic model that solves everything for you. And that was the whole purpose behind our course, to just show you that this math, it breaks, it has capabilities, we have theoretical limits on optimization, we have practical limits on optimization. We have theoretical limits on how much training data we have. We have many aspects that govern our system. So don't just think that, yeah, let's try to learn everything end to end, for example, which is a very fancy word that's being used right now. No, that's not always the best solution. Think of your problem. Sometimes you just need logistic regression to solve your problem, and you'll basically be hunting a rabbit with a cannon, and you shouldn't be doing that, right? Okay, so let's discuss the methodology for designing a deep learning model. First of all, you need to determine your goals. So what is the error metric that we want to use? This is the most important thing, because without a quantitative result of your model, you can't know how well or how bad you're performing. And your target value to this error metric. Now, where do we get this target value? For academia, it's easy. You go to baseline website, you check the table, you see the best performing method, and you try to beat it. Of course, you check the best performing published method, and you try to beat it. Right? For application engineers, it's much more difficult. For example, when you try to develop object detection algorithms for autonomous vehicles, is mean AP a good enough guarantee that our algorithm will be safe, for example, on the road? No. So you need to specify certain, for example, you need to specify the mean average time between failures. That's one good metric for applications. If your algorithm fails every 2 seconds, then there's a huge problem. And you should, even if the mean AP is very high, you should be wary that maybe you're just overfitting on the training data, right? Or on your data set. So let's take our team as a case study. So this is the first thing that we did, right? We determined and coded up the evaluation metrics. The second thing that you should do is to establish a working end-to-end pipeline. What does this mean? This means that you code up a skeleton code with minimal regularization, with the most simple optimization. You just code up a skeleton code that is trainable as soon as possible. And why is this? Why should we do this? Jason and Melissa, why should we do this? Because of the problems that we face that we did not anticipate, right? There are many problems or many issues that we might face that are not that cannot be anticipated prior to starting the project. So one of them is the issue that we face today, like how we should do the orientation, for example, for angles, thing that we discussed today, right? So that is one very important thing. As soon as possible, end-to-end system, even if it was just a system that has been published before, just make sure that this system works. And after that is the whole gist of this lecture. We will discuss this portion, how to instrument our system to determine the bottleneck performance. So what happens if the loss function is not decreasing? What's the cause of the loss function not decreasing when training? What happens if the training error is high, or the training error is low, and the validation error is high? What happens if the training error is high and the validation error is low? Which is a very real case. We'll talk about it. And after that, this is very important, incremental changes. So you don't fix your system by changing the model, augmenting the data, adding regularization, changing the optimization in the same run. This doesn't benefit you at all. You just created a new system and you're stuck in a loop. You don't know what's going on. Incremental changes. For example, you have very low, or the training error is still high. It's not low enough. You increase your data. You collect more data. You increase the capacity of the model. You augment your data set step by step. You improve your optimization algorithm, but you don't do them in a single run. And this is the methodology that everyone should follow when designing any machine learning algorithm, basically, not just deep learning algorithms. Okay, so let's start with determining the goals of the system. So the performance metrics. So determining which error metric to use is the most important first step for designing a deep learning system. This is because your error metric will guide all your future actions. This is very important. If you code up this error metric wrong, you're done. You're basically done, right? You will be erroneously estimating that your system is working well when it's not working well. Then you go deploy it in the field, and it will fail. So make sure that you don't mess up this step. This is very important. If most probably you'll find the source code online for most of the error metrics for most of the AI complete tasks that we have right now. So just use that. You don't have to code your evaluation metric. And if you have to code your evaluation metric, unit tests for everything. The second step is to determine the value of the error metric to be, which is also really important. So you get this value of the error metric from academia or from your design specifications, and you start designing to beat this value. And keep in mind that for most applications, it is impossible to achieve zero error. Why is that? Why is it impossible to achieve zero error for most applications? Come on, it's the end of the book. worse.
Your labels might be wrong, like your branch root labels for your dataset.
Ah, that's a very, like that's an action. What's the? It's in the nature of our machine learning algorithms. It's the base error that if we have perfect optimization, infinitely many training data points that are independent, if everything is perfect, we still have the base error. The base error is the minimum error that we can achieve using our system, right? So don't assume that you will achieve zero error. That might not be the case. Okay, so the most common reasons for not achieving zero errors is imperfect optimization, not enough training data. The real data distribution is not part of the model distribution family. And these are just a recap of the whole course. Right? So if we're trying to fit a unimodal Gaussian distribution to a multimodal Gaussian distribution, we'll never end up achieving zero error, right? Ever. Because our actual distribution family is not in our model family. Even with infinite training data and the ability to recover the true data distribution, there is a minimum error bound that the system can achieve. Base error. Less known reasons for not achieving zero error are: one, your system might be perfect, but your input features may not contain complete information required to describe your output. For example, I tell you, I want you to create a red blob detection algorithm. Red blobs in images, but these images are grayscale. Like, how can you achieve zero error? You can't, because your input information does not contain enough information to determine your output. And this is very important. The process to be estimated might be inertly stochastic. So the noise might not be even consistent in our model. So the question is, how can we determine the minimum performance measure that is required? And I answered that in my previous slide. So in academic settings, you have a standard benchmark for almost all applications. And you just go there, grab, see these benchmarks, see what the best performing method is, try to meet it. And keep in mind not to compare apples to oranges. That means that sometimes, for example, when you have two machine learning algorithms, you need to make sure that these two models are trained on the same data. That's one. Two, you do not compare ensembles of your model to single networks of other models, because your ensemble will almost always perform better. Third thing, when, for example, some people even consider normalizing your input, so zero centering and divided by standard deviation, should be done for both systems. Some people just think that this is part of the architecture itself. But some reviewers in conferences will tell you that you normalize, that guy didn't normalize, maybe this is what's giving you like a performance boost, right? Usually dropout, usually batch mode, these are considered parts of the architecture. So we don't, and training method, for example, backdrop or auxiliary losses. People won't bash you for using these and then comparing with other algorithms. In the application setting, we usually have some idea of the error rate that is necessary for an application to be safe or cost-effective or appealing to customers. So in this setting, we go full out. We do whatever it takes to gain this performance boost. We do not just say, oh, I don't want to regularize right now so that I can compare. No, do everything that's required to gain your 1% boost in performance. This includes ensemble models, this includes dataset augmentation, any form you want. This includes empirically determining thresholds, whatever is needed to gain this performance boost. Okay, so Any questions about the performance metrics? I'm just going to go through a little bit of a discussion on the default baseline models that should be used, and have like some examples for certain aspects of what we are doing. So, after choosing performance metrics and goal, the next step is to set up a reasonable end-to-end system as soon as possible. And this is really important. So, some recommendations for default baselines based on my modest experience with deep networks. And just one thing, keep in mind that deep learning research progresses very quickly. Whatever you learned in this course, everything you learned in this course might be obsolete in 6 months or 5 months. Every paper you read will have a paper that beats it in 6 months. That's how deep learning research works. So it's very important to keep up to date with the latest state of the art, or what is considered our default go-to baselines. For example, this was VGG16 for object detection 3 years ago. Nowadays, it's resident on 1. That's the default feature extractor that we go to for everything, basically. And this is the thing I told you before. You should never use a Canon to hunt a rabbit. You should never, ever try to just use deep learning for example, classifying binary data with two-dimensional binary data, for example. You have x1 and x2, and the output is 1 or 0. We do not need 101 convolution layers or fully connected layers to actually classify that. And depending on the complexity, you might not, or you want to use deep learning at all. And so there's a subset of problems called AI complete problems. If your problem is not in the AI complete category, most probably you can be much better off with logistic regression, just pure linear regression for regression stuff, or with linear SVMs. So, what are some examples of AI complete tasks? Or how do we define AI complete tasks? So, AI complete tasks are tasks that cannot be hard-coded. And that require at least, so I'll discuss this later on. What kind of problems can deep learning solve? So you cannot tell me, oh, I want to train a model to write philosophy papers, similar to or to discuss whether an autonomous vehicle should run over 2 little children or 1 old lady. Like, this is not. So deep learning cannot solve anything. We'll discuss this. We'll come to this. Okay.
Well,
There might be enough training data.
there is actually a research from University of Connecticut, where they use machine learning to make ethics decisions and integrate it in a robot. Anyway, and they were actually for medical. This was for medical context, and they were pretty good. They were comparing it with
at least juries and judges.
They were better. Yeah, they were better. No, they were feeding it with cases, and they were better than sort of rules that people came up with sort of off the cuff. Medical professionals. They could have come up with better rules by studying carefully the cases. The machine learning was just basically helping them with analysis of the cases. That was all.
We'll come to what deep learning can solve currently, the current state of deep learning. Not in 50 years, but this current state of deep learning, what can we solve using these networks? So if your problem falls in the AI complete category, choose the base architecture based on the structure of the problem.
Sorry, can I just ask, is there a definition of AI completely and NP complete?
No. AI complete is an informal way. It's similar to NP complete. So, what it's informally saying that if you can solve any AI complete problem perfectly, you can solve all of them, right? So it's like, for example, speech recognition, or object detection, or what else falls under semantic scene understanding, any form of semantic scene understanding. These fall under AI complete tasks, because even though you're doing, like, even though we have reliable systems that can do this task right now, they have errors that are based on stuff that we cannot interpret, right? Like stuff that we don't know how to feed the network this kind of intuition, so that it, and that's basically it. So
yeah, so there's a slightly another link, which is the one characteristic of NP-complete problems is that when you get a solution, you know it's a solution. So it's a hard problem. So like when you classify an image, you know it's classified, right? So
yeah, but you don't have systems that are reliable enough to classify every image, or to that's the kind of. So I would like to think of it as stuff that cannot be hard coded. So there's no specific set of rules that can be serialized in a program in which will always work for our scenario, right? Hence, human beings can basically inscribe their knowledge or their manifold learning basically into a set of lines of code that are fixed. So, okay, so for supervised learning problems with fixed small-sized input vectors, you will most likely end up using forward fully connected networks. For input variables that have known topological structures such as images, voxel grids, or sound waves, for example, that are sampled at discrete intervals, we use feed-forward convolution neural networks. For problems with input that are sequences, trees, graphs, we should use gated recurrent networks such as LSTMs or GRUs. So LSTMs.
Sorry, what was the middle part?
Here?
Yeah.
It's just any input with topological structure, like images or voxel grids, or and for unsupervised learning problems, the default baselines right now are variational autoencoders. You have it depends on the problem. This is a very, very understudied area in machine learning, just because 99% of machine learning application development is here. So if you work in a company and they want anything in terms of machine learning, they will come and tell you, you need to provide me something, one of these three architectures. Variational autoencoders and generative adversarial networks basically are just research curiosities so far. Google is heavily invested in GANs right now for learning, because you have the ability to learn input distributions, basically, which is really impressive. So the exact baselines for certain tasks that we are working on. For example, for image feature extractors, we use VGG16, ResNet 1.1, or Inception v3. And this is, so the performance goes like this. VGG16 performs the worst. ResNet 1.1 performs a bit better, and the best performing feature extractor right now is Inception v3. However, this guy is a bit slower in inference than these two. The de facto standard is ResNet 1.1. However, VG16 is very conceptually easy to visualize and understand and to train. That's why people still stick with VG16. And it has cafe, and so literally every library has an implementation that you can just take. For object detection baseline models, faster RCNN is the most used currently. Faster RCNN that uses ResNet 1.1 as a feature extractor, basically. YOLO is extremely popular just because it's very, very fast. And there is the new RFCNs that are also being pushed right now. And for semantic segmentation, you have segment and fully convolutional network. These are the standard. If you have this task and you just don't want to think about it, you just go grab this, train it on your data set, and you're done. You're good. For optimizers, Adam or Adam as a problem, both with indicating learning rate. These are the factors. Don't try to like invent a new optimization algorithm if you want to train a neural network. Just go use Adam. It's implemented literally in every neural network library, and this Adam is very robust to the initial choices of hyperparameters. So you probably will be good by just using that. Regularization, early stopping. You should always use early stopping at all times. If it's not embedded in your code, that means that if you did not code early stopping so that you monitor your validation error and when it starts increasing, you got just save snapshots of your model and evaluate them later. So that's one other way for early stopping. Dropout is very easy to implement, and be careful to try batch norm since it might remove the necessity to use dropout. So batch norm, dropout, and early stopping. Parameter norms need, so penalizing parameter norms should be left out till later because they tend to be hard to interpret.
So what was again the explanation why batch norm would sort of replace dropout?
So batch norm, what it does is that it basically you can't use batch norm and dropout in the same. Why is that? Because batch norm, what does batch norm do? Batch norm keeps a moving average of the statistics of your activations, and it makes sure that your activations are normalized after each layer, right? Dropout kills some units, and killing these units will interfere with your the statistics of the activations, right? So when you keep a moving average using dropout, what you will be keeping is the wrong moving average to be used in
so it's not that one is replacement for the other. They're both regularization techniques, but they're just incompatible.
But most of the time, they found out that batch norm works better than dropout, and it's much easier to keep track of and implement. Dropout sometimes makes the network inference and backbone a bit slow. It depends. It depends on your application. That's some people just use dropout, some people use. So this is the artsy thing about deep networks. There's no standard. You need to try. This is a hyperparameter. Try both, see what works for you, and use it. Okay. So these are the default baselines. Now, what will happen after we finish our default baseline? We test the baseline. When we test the baseline, we have different outcomes of our test. So, the training set error remains high. That's the first outcome. The training set error decreases, but the validation set error remains high. And both training and validation set errors are low. One more scenario is when your training error is very high, your validation is very low. That's just a no-go. Like, you can't interpret anything from that scenario. You might just like be lucky. Just it has some ways that work for your validation. So this is a flowchart of the design process. You determine your performance rates, establish a working end-to-end system. Is the training error high? You do some stuff. Is the validation set error high? You do some other stuff. And we'll discuss what these are in detail. And hopefully, after you minimize the validation set, you're done. Not really. We'll discuss this later on. This is the beginner's guide to the design process. However, experts have, like, for example, Andrew Neck provided an alternative model for this. Just because people tend to really underestimate the discrepancy between the probability distribution of your training data and the probability distribution of your test set data. So this is your training data. This model done here assumes that you have your test set, or your test set has the same probability distribution as your training set, or as your test set has been drawn from the same probability distribution as your test set, right? This is not the case. 99.99% of the time, this is not the case, and we'll discuss where this model breaks. So, first thing first. You finish your end-to-end baseline. You try to overfit on 100.
Sorry, I didn't get that last comment. I can see how my training or validation set might not reflect reality, but I mean, I can certainly engineer the training and validation set to have similar distribution or not.
Okay. No, it's very hard. It's very, very difficult.
Well,
actually,
but, I mean, like, how about just random sampling?
Doesn't work. We'll discuss. Why isn't that this?
It'll still be a divergence, two separate populations.
So it's
Sure,
not.
yeah.
It's not you who decide.
It's not because
Yeah.
you don't. It's because you're drawing. They are drawn from the same.
They're not drawn from population. I see.
Yeah, so but no, you can draw. You can draw you can draw from the same population, and they have the same distribution. Meaning they are drawn from the same distribution, but the actual population you draw
Exactly.
is different.
So the training set.
Almost by definition, different because it's a different.
Yeah. So our test data, for example, let's say object detection. The test data is drawn from the natural image distribution, which is something that we cannot learn. Our training data has its own statistics, right? It might resemble the natural distribution that we see in the wild, it might not. And this discrepancy is what breaks the validation set error. So sometimes you will have a validation set error that's low. You go and test, it fails. Your system fails. Why is that? People will just, oh, the validation set error is low, why did it fail? I'm going to go through that in details in 5 minutes. So if your training error, so you try to overfit on 100 images or 100 training data points, you fail. Your training error simply does not decrease at all. 1, is the optimized code running correctly? So first thing to do, if you implemented the gradient functions yourself, is doing a gradient check. A gradient check is computing the gradient in the backprop operation that you have coded. So you coded the forward and backward pass of your layer, right? You compute the backward pass, and then you numerically compute the gradient, which is delta f of x over delta x, right? And then you check if these two are close to each other. They will not be the same, but they should be at least close to each other, right? That's a gradient check. Most probably you'll never face this problem just because it's very rare that you actually implement the layers yourself, right? One other thing is the learning rate correct. What happens if the learning rate is too high? Which is you're basically knocking weights off the manifold that you're trying to learn, and you will never recover. Right? We discussed this like the first lecture. Remember? Yeah. You will never recover. You're just killing your neurons, and then the training error will never go. Will never drop because you're done. You are knocked off the manifold that you're trying to learn. Does the model have high enough capacity? Do you have a single layer and you're trying to learn object detection, KT, for example? Might be the case. Make sure that, so this is really by just trying to overfit a small portion of the data set. 100 images is too low. So you should just try like 500 images, for example, try to overfit and get zero training error, and then you can go and train on the whole data set. Did you train for a reasonable amount of epochs?
This question. Didn't you say that we cannot have a zero error?
Not so. This is the training, is the loss. The loss can be zero. Why? Because we are not, the loss is not mean AP, mean average precision, right? The loss is a function for object detection. What is the loss? The loss is classification error, cross entry, right? If you correctly classify every instance, you get a zero error, right? And this is easy. Why is this easy? If you have two images in your training set, you can overfit those from 1 or 2 passes, right? And then you'll have zero error. The zero error that I was talking about is the actual metric that you are using, like mean average precision, mean IOU for semantic segmentation, right? These non-differentiable performance metrics, we cannot have, we usually don't achieve zero in those methods. However, the loss function, very easy to achieve zero on the loss function, right? So did you train for a reasonable amount of epochs? Like, did you go through your data once and assume that everything will work? And, so most probably you'll never face that unless you really don't know what you're doing, because early stopping, right? You just keep training until your validation error starts increasing. If all else fails, you need to rethink your architecture. This is like, we will face this in every slide from now on. This is the trivial solution. Oh yeah, rethink the architecture. This is one of the hardest solutions for your problem. Architecture, designing a new neural network architecture is not something easy at all. And we are facing, you know what I mean, like you will be facing many problems. Okay. So, these are the standard issues with high training error. Most of the time, it's learning rate. You just lower your learning rate a bit and everything works. Okay, so we finished the training set error. We go to the validation set error. You train, you get a low training set error, but you end up with a high validation set error. What's happening? Overfitting. So, how do we remedy overfitting? One very important thing. Do not start collecting data if your training set error is high. Okay? Do not go and start, yeah, let's collect more data maybe. No. If your training set error is high, there's something fundamentally wrong with what you're doing. Because you should be able to overfit on basically any data set with your neural network. First thing first, you collect more data. You can collect more training data and label them if you have a big company with 1,000 people labeling your data. Or you can do data set augmentation methods if you're a small lab like us. The second step is employ regularization strategies. Many regularization strategies to be employed. Try them all. Hyperparameters, dropout, batch norm, injection of noise at the input level, right? Path drop, auxiliary losses, multitask learning, parameter sharing. You have like many hyperparameters that you can do here. And if all else fails, then you need to rethink the architecture again. Now, what if nothing helps? And this is where we were talking about. So there is a very pathological case that is basically unknown to deep learning practitioners in academia. And this case is illustrated at the validation set having a different distribution than the actual test set. And this case motivates us to rethink the design process so much. And this is actually the new design process that we should think about. So, first of all, you determine your, so do I have a pen? Here, yeah. Let us just discuss this. So, human error. What's human error? The human error is the error of subset of human beings on the task at hand. So, natural language processing, you get a human being, you have them listen to your speech, and you have them to write up or type what he hears, right, or she hears. That's human error. And this is very, very useful. You'll see why. The second one is training. Training. Let's call it that. So let's separate our sets. We have the training set. Let's say we are doing end-to-end learning of autonomous driving. We have 50 hours of driving. We take 2 hours, and this is called the dev, and this is called the training. Okay? We then go and collect more data randomly in our test environment. Okay? And we'll have like 16 hours of test, and you also take our test dev. So this is basically the validation set. Let's call it dev for now. This is great. And this will be 2 hours. So this will be basically 48 hours, 2 hours dev, and then this is the same.
So you said, you go and collect these 16 hours randomly. Maybe at some point later, it'd be also nice to talk about, actively and not randomly collecting data.
Yeah, that's good. So let's give a real life scenario. This might be Kitty data set. This might be Google Drive. Okay, different statistics, different everything, right? So that's what I mean when okay. So if you basically collect your test data in the same area as your training data, then you're basically doing nothing, right? Yeah. So we have the human error. Let's say humans, very good drivers, they mess up 1% of the time. Okay. If our training error is much different than our human error, let's say 10%, what does that mean?
Yeah, we have a poor system.
That means there is a huge bias. Remember, the bias varies, very informal. Statisticians will kill me if they hear me saying this, but this is high bias. Training depth. Let's say we have 10.4. This here resembles our variance, basically. So this is very high. Then our model has very high variance. Now, for traditional machine learning people, this is what, or for deep learning practitioners, basically, this is all they know about the data set, right? We either have bias or we have variance.
Sorry, what was dev again?
Validation set. Let's. Yeah, it's the validation set. Yes. Now, what if happens if there is a discrepancy between the training depth and the test depth, or the training validation set and the test. Sorry, this is test and then test. No. Yes, depth.
Sorry, I didn't quite. I mean, I remember the discussion of bias and variance, but I can't map it to here. I don't know exactly what it means.
So, bias. Let's we not have time to go through the discussion again, but let's quickly recap. So bias is in this scenario. Let's listen. Bias is how much our system is different from human performance. Okay. Variance is how much our system makes errors on the validation set when it's trained on the training set.
Yeah, there's little, right?
Yeah.
Because it's the same, right?
Yeah. It's not the same. It's a
Well, it's
subset.
10%. No, I'm talking about.
Okay, here it's very good.
Yeah.
For the scenario, it's
the
very
variance,
good. But if this is 20.1%, then
yeah.
what are we doing? Then we are overfitting.
Yeah.
Variance is overfitting. Implies overfitting.
Okay, so
Bias implies collect more data. More data if you have consistent estimators, which is 90% of the time is not the case, or try to figure out a better architecture to close the gap between human performance and. I'll come back to human performance in 5 minutes. Why do we use human performance? Now,
well, I still don't understand. Like, if you have 10% error, I mean, like collecting more data is not going to help you. I mean, maybe it seems more like why.
maybe it helps because maybe there's some scenarios in feature space or some areas in feature space that have not been covered by.
Yeah. So basically, you're saying that. Well, yeah, but it's a training set. So I mean, you train it, and then like if it doesn't learn this thing, so what? How more data is going to help you?
So that's you have a point. So the bias here. Okay, let's say modify the architecture.
Yeah.
Instead of increase the capacity. Okay. Let's say increase the capacity instead of okay. Here we collect more data at the variance level. Let's say that there is a huge gap between the training depth and the test depth. Remember, the test set, we don't have access to the test set. Test depth, we have access to the test depth, we can evaluate. Okay? So, Kitty, our card, for example. Okay? If this is 50.1%, what does that mean? With respect to like absolute. What does that mean?
Well, that's not representative of the original.
Exactly. That means that
data.
the distribution for this data set or for the training data set is so different from our test data set. What's the remedy for this?
Well, you
Very
have to get more data for you.
Get labeled data that resembles your training set, your test set, which is really good. And here is where actual few-shot learning, domain adaptation comes into play, which are stuff that most people don't even consider when they're working in deep networks. The final error is the test error. So we have a test set that has been labeled 200 images, and water, for example, and we try to measure our performance on this data set. If it's too high, so let's assume that we got 10.1, 10.5, everything is perfect, and then here it's 15.2. What's happening here? Here you are overfitting on the depth set. How are you overfitting on the depth set? How do human beings overfit on depth sets? On the validation set? You just keep tuning the hyperparameters until you get a really good configuration on the validation set, and you assume, oh, this is the good configuration, let's go test it. Right? And then you need to figure out where this overfitting occurred.
Well, you need to gain more data there.
This is a different overfitting mode than this guy here. This overfitting mode is human overfitting. That means you have tailored an algorithm that works perfectly on your validation data set, but then it doesn't work outside the data set. You have made design choices to get the best performance on this specific validation, which is what people are doing right now, literally in every single area of research, right? 90% of papers right now overfit on data sets without them even knowing, just because the data set
because the cost of having another data set is yeah. So I mean, the idea is that of course, like if I have something, it's a good example. I trained in Europe and I go to California. We're gonna have to adapt for the wider sky, but that doesn't mean that it's gonna go and work in Australia. Well,
exactly.
You have to go and train also in Australia,
exactly.
right? I mean, the question is how many countries have to train it until you can say that, oh no, that's now gonna work everywhere, right?
And that's why people are so optimistic that autonomous driving will be like this. Kitty has been collected in one city in Germany. Everybody is using Kitty to do everything. How do you expect one city in Germany to resemble the whole world, right?
They don't.
Yeah, exactly. But that's what people are expecting. They train on Kitty, they're like, our system is the best, it works. No, it works on one city in Germany, one city for training and test data. Basically, you have very similar distributions. Good luck trying to have it work in Lebanon, for example. This guy knows.
Even for humans, I took a lot of time to learn how to drive.
Exactly. Exactly. Even for human beings, going from one area in the world to another, it requires a bit of time, 5-6 months, to get used to the rules and regulations and the cars, the streets, the signs, everything. And this is very dangerous because usually everything stops here because nobody has the test data, right? They usually have either the same distribution in terms of test data or a very small amount of test data that nobody does. Nobody does use it. For example, a recent paper in CBPR, MP3D, right? It stopped here. They evaluated their training dev error. They got better than other people, and they're like, "Oh, we're good." This is overfitting. This is the best result of dev set overfitting. You basically can overfit the dev set by just choosing your hyperparameters to give you the best performance. Okay. So this is our new design process. We go, if the test validation set error is high, if this guy is high, we gather data similar to our test data, or we go to data synthesis, which is what I prefer. Having seen people label data, having labeled data before, of course, every graduate student goes through labeling data, right? Yeah, but people can't tolerate labeling data, as we have seen in our lab, right? Yeah, people can't stand labeling data. So data synthesis is a very important research direction. Synthesizing new data using simulators, using, I'm not going to discuss this right now, but we'll discuss this later. Okay, and of course you can always redesign the architecture, right? And hope that your new architecture works. And finally, if the test set error is high, you go gather more test validation data because you have overfit on your test dev. Basically. So you expand your test dev and you see what's going on when you expand your test dev. And hopefully when this is done, you will get a system that can actually be used for real life application.
Which are you saying at that end step that you're probably pretty confident that your architecture is fine?
If you perform well on the test set, you're done.
No, I meant like, let's say you don't perform well on the test set. Like everything is good up until say test validation set error.
Yeah.
And then on the test set error.
Your architecture is good enough to fit the training data, which is what you want. However, it's overfit on the test dev, basically. So you have tuned your hyperparameters too much for this specific data.
But at that point, you're pretty confident
that your architecture works.
Okay.
Okay.
I
it's not a guarantee,
It's
right?
not a guarantee, no.
Because if you add more data, maybe now actually
You see that
you need more capacity or something, you know, in the architecture.
Maybe you added the new, for example, your test def comprises of non-oriented objects, and then you go test your test data. It has oriented objects, and you fail. Then you gather data and you see, oh, there's oriented objects here. No, that means your architecture is not working out. That means you need to revisit the earliest stage, where you need to either gather training data containing oriented boxes, testing it, it might not work, and then you have to reiterate. This is an iterative procedure, right? Iterative procedure. So we go, get a bigger model. Doesn't work, we go back here. Training longer, doesn't work, we go back here. Any questions about this design process? Everything working out well? This area? Okay, we still have 20 minutes. Very quick discussion about hyperparameter selection. Since now we have I'll mention something very, very, very fast. So a big trend right now in big companies for machine learning is that you have a machine learning team and you have a high performance computing team. Okay? It is really difficult for a single human being to learn everything about machine learning and high performance computing. However, this trend shows you that machine learning and high performance computing are very interrelated. And having high performance computing power, it's very essential for actually developing good machine learning algorithms, as we will see with hyperparameter selection. So, choosing hyperparameters, the first method to choose hyperparameters is choosing hyperparameters manually. This is very difficult because it requires you to know exactly how the hyperparameters work. So if you don't have very good understanding of how these hyperparameters affect your algorithm, you probably wouldn't be able to. This method is used by people who don't have much computing power, because when you go to automatic hyperparameter choosing, if you have enough computing power, you can just throw a wrapper around your deep learning algorithm that injects random hyperparameters and you do much better than this guy here. Anyways, the primary goal of the manual hyperparameter search is to adjust the effective capacity of the model to match the complexity of the task. Effective capacity. You remember what effective capacity is versus the actual capacity? No? Should I? Yes or no? Okay. Well, what's the effective capacity?
I guess based on the current parameters, right?
So we have discussed the capacity of the model as in the number of parameters, right? But is this capacity the actual capacity of the model or the effective capacity of the model? No. Why? Because regularization. Because imperfect optimization, right? Because missing labels, missing data. This is not the effective capacity of the model. So the effective capacity is governed by three factors: the representational capacity of the model, which is the number of parameters; the ability of the learning algorithm to successfully optimize the cost function. Good optimization algorithms that can search your space and converge. And the degree to which the cost function and the training procedure regularize the model. So next, I will show some common hyperparameters and their effect on the effective capacity. Number of fitting units. What happens if we increase the number of fitting units, guys? The representational capacity increase, and it's written right here. You can actually, and the number, and then the effective capacity increase. What's the negatives of increasing the number, or of increasing the number of fitting units? It's more memory, and it will essentially increase the computational cost and memory cost of every operation in your network. Forward pass, backward pass, computing cost function, everything will increase.
So it might be also more difficult to optimize, right?
It might be more difficult to optimize. Convolutional kernel width. If we increase the width or height of the convolutional kernel, will it increase the capacity or decrease the capacity? what happens when we increase the convolution kernel? There's more parameters. More parameters, it's the same effect as the number of elements. It's different mode of effect. A wider kernel results in a narrower output dimension, reducing the model capacity unless you implicit zero pad to reduce this effect. This is the major difference from the above. So it increases the capacity as long as you zero pad. If you don't zero pad, you'll be shrinking, and your next convolutional kernel will be smaller. Wider kernels require more memory for parameter storage and increased runtime, but narrower output reduces memory cost. So this is a bit iffy. It depends on the zero padding. If you zero pad and you don't zero pad. Implicit padding. So it's the same thing, except that so it will increase your capacity just because it keeps the representation size large across layers. When you zero pad, you're maintaining the size of layer.
You're losing detail.
Yeah, yeah. And you have to choose if you want to pad or not. Usually, this choice is directly coupled with the choice of using max or pooling or not. If you don't use pooling, you skip padding at certain layers so that you shrink your dimensionality of the input. If you use pooling, like in DBG16, you do not. You always zero pad, so that you maintain your convolution layer and then you shrink using max pooling. And weight decay coefficient. So decreasing the weight decay coefficient frees the model parameters to become larger, and it will increase the effective capacity of the model. Of course, right? You know what this means. This is the lambda before the parameter norm, right? Dropout rate. Dropping units less often gives the units more opportunities to conspire with each other to fit the training data set. So if dropout rate, you know what dropout rate is? It's usually 0.5. If you make the dropout rate 0.2, it's parameters have more chance to interact and to overfit your training data, right? And finally, the most important hyperparameter. If you have time to optimize only one hyperparameter, always go for the learning rate. This is a chart that shows what it looks like. This is the training error loss. Very high learning rate, you will basically diverge. Moderately high learning rate, you will converge fast, but then plateau. Lower learning rate, you will convert, but it will take you a lot of time. And this is a good learning. Usually what happens is that we have a learning schedule, right? This is very important for people who are going to just start training the neural network. Learning schedule means that we have a high learning rate up to a certain point, and then we decrease the learning rate.
Could you infer that the low learning rate will eventually improve on the good learning rate in terms of loss?
If you have infinite time. It really, this is very iffy. Like you cannot just say this is the correct, this is just a hand wavy way to explain this. But a low learning rate, usually it's better to have a low learning rate. However, it will take too much time to actually go anywhere. It will take, like, you don't want your network to be training for 5 months, right? That's the thing. That's why we have a limited time, and that's why we tend to compromise. And even if we achieve the training error that is lower in 5 years, we don't want that, right? We want something that's right now, and that's why we use the learning schedule. Usually, we have a learning rate that is pretty high at the beginning, and then we decrease it by an order of magnitude after n or k epochs, basically. And we showed you the linear learning schedule, right? And optimization.
And I assume that hundreds of things have been tried here, right? Like, adaptive learning rates, detecting when you're diverging, right? All this kind of stuff. Randomness when you hit the stable equilibrium early. There's all kinds of stuff you can play here, right?
That's exactly it. That's why you spend time optimizing this hyperparameter. And the very special thing about the learning rate is that there's no such thing as a high or a low learning rate for our model. Our model performs the best if we choose the correct learning rate. So you can't just increase the learning rate and assume that the capacity of the model decreases. There's no such relation. No. The relation is the model achieves optimal capacity if we choose the optimal learning rate. And that's why you spend so much time on optimizing this hyperparameter. These are basically what I talked about. The effective capacity is the highest when the learning rate is correct. And that's it about manual tuning, basically. One slide about automatic tuning, hyperparameter or hyperparameter tuning. Two ways to automatically tune hyperparameters. You take, for example, let's say the learning rate between 0.3 and 0.003. We take an interval, logarithmic interval, of 10 points between these two lines, and we do a wrapping around our learning algorithm. And we train a separate network using each learning rate. What's the disadvantage of this?
You're training a ton of networks.
It requires high power computing. This requires a lot of time, a lot of effort. Usually people with huge servers, training servers, can do that. It's similar to what Nima is doing right now, right? You require 7, 8, 10 GPUs to actually do that separately. And then, so it's very consuming. The second way, which was proven to be better by, of course, Joshua Bengio and his lab, is randomness. So you select two points and you uniformly sample up to a certain number of samples, and then you train. This is better. Why is this better than constant intervals? Let's draw a figure.
Well, you could also do sequential sampling, right?
The first one was sequential sampling. Oh no, the first one was.
So sequential sampling would be basically looking at well, your uncertainty and your gain.
So let's draw this. People will understand this right away after I go. Let's assume we have a learning rate and we have our performance. So this is performance. And this is learning rate. And it's a function that looks like this. Okay. This is interval sampling. We're taking an interval of 0, 1, 2, 3, 4. Random numbers. Not correct, but between 0 and 4. So we take this, 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 and this. Okay. So you can see that the interval sampling versus the random sampling, right? When we take many samples here, it is much more probable that we achieve our best performance rather than taking intervals. Because intervals, when you take intervals, we might skip a very important feature, right? Just because it falls exactly in the area that we don't sample from. And this is like you think of this as a very hand-wavy way, but it has been proven. There's a paper on random hyperparameter selection by Bengio's group. Okay.
But I mean, if you're resource constrained, I would use sequential sampling method.
Of course. If your resources are constrained, but what's the good thing about this? You not need to know anything about the hyperparameters. Literally nothing. You can just know nothing about the hyperparameters, feed an interval, a large interval, huge interval. You just need to know two hyperparameters, the beginning of the interval and the end of the interval, right? And these are much more intuitive to deduce because you can read the paper and you're, oh, these guys use 0.3. Let's take between 0.5 and 0.02, for example. Just, right? Okay. So that's for automatic hyperparameters. So this is grid versus random search. This is exactly the figure that's here. And let's conclude. So the conclusion is deep learning is a black box that can solve everything. Am I correct or not? This is what you conclude. No. No. The current state of deep learning allows us to tackle inference tasks that can be done by humans in less than 1 second. That's the current state of the deep learning. When you talk about ethical or moral problems, you cannot determine that course of action in 1 second. And hence deep learning is not a good model that can be used for that. So, for example, walking. Does it take you more than 1 second to think about walking? Deep reinforcement learning can solve we can teach systems how to walk, basically, via deep reinforcement learning. Object detection. You look at a cup, you look at a person. Does it take you more than 1 second to determine this is a cup, this is a person, this is a chair, this is a... Then there's something wrong. No, it shouldn't take you more than 1 second to actually determine that.
Well, but I think there's also a difference between 1 second to decide versus how much time it takes to learn.
Exactly.
It should be also different.
Exactly. So this is the inference tasks, right? It's the inference stage, not the learning stage. Driving. Don't you sometimes you phase out while you're driving and you just arrive at your location. That's why that's why driving, like end-to-end learning for driving command regression is very attractive. Because if humans can do it without even thinking about it, basically you turn off your brain and you just observe, your eyes observe, some process is happening in your brain and you're automatically driving. You're thinking about something completely different, right? And you avoid obstacles and you arrive to your location. It also allows us to tackle a very important subset of tasks. That is very, very, very important and very, very, very underestimated in deep learning research. It's prediction. It's predicting everything. Predicting what action comes next. Predicting what word comes next. Generative models. So when you have a data set, a trend, for example, economic curve, and you need to predict if the stocks will go down or up, deep learning can help you do that. Can solve this task. In context of autonomous driving, action prediction, right? Deep learning models can predict the next optimal action to make. So the conclusion of this course is that deep learning is a set of mathematical tools, and as with any other tool, it can be misused. Be very careful when later on you want to decide if to use deep learning or not. Be very careful if your task requires deep learning. It's not a black box, and it's not something that's magic. It's math. Everything is understood, well understood. And this is just an introduction to deep learning. There are many important concepts such as unsupervised learning models, few-shot, one-shot, and zero-shot learning. This is very, very, very nice. Domain adaptation, adversarial examples, generative models have not been covered in this course. Hopefully, if we were to do this ever again, we're going to include generative models in the course. And finally, you should know that there is a very high probability that whatever was discussed in this course will become obsolete in 6 months. So keep reading papers, keep up with the state of the art. Don't just think that this course is like, we know everything about deep learning. max pooling, for example, it was a trend 3 years ago. Now nobody wants to use it anymore. Jeff Hinton says it was a big failure. It was a mistake. It's an embarrassment that it works, right? So stuff that are being used right now might not be used in 3 years. Okay, and that's it for the course. Thank you for listening.
That was wonderful.
Nice work, Ali.
Yeah, one question. In terms of training, like, usually you do your random batches and so on. But when you think about training for humans, you have actually pedagogy, which means you have actually some sequencing experience that would present to a human. You would teach certain concepts first, and then you want them to teach other concepts. I wonder, at what point this becomes, is this something that's going to become of interest for more multitasking or for architecture architectures? I see that there's some ideas out there, like if you do like multitasking, we can train your first network, and then
so there's
train your next network.
Supervised or unsupervised breeding.
Unsupervised what?
Greedy pre-training, where you train each layer of your model to do the same task that you want the final layer to do. That way you can think of it as like teaching the network lower average.
Yeah, I'm just thinking that if you want to properly initialize, so to speak, your initial thing, so that it can take you to the next step. But I don't see that being exploited a lot.
The thing is, many people are attracted to the end-to-end fashion, which is not something good. Because sometimes intermediate intervention or injecting human bias in the intermediate level is not something bad, right? But many people are just so attracted to the end-to-end. Exactly, just like let's collect infinitely many data and just let the system do whatever.
Instead of running and going,
exactly.
go to the bar.
Exactly. So that's why people are lazy. Like people don't want to tackle, for example, there is stuff like curriculum learning, learning schedules, teacher forcing and professor forcing, but nobody wants to actually go through that except like in the world, just because there's no funding for that kind of stuff. All the funding is on application, not on, right?
Yeah, but I'm pretty sure that in the future this is going to be
hopefully.
This will be an area, because this kind of, this random approach, it's like a brute force approach, and it's.
How do I read?
But I think once this